Aloha, everyone. My name is Alexa Anderson, and I'm a third-year PhD student at the Institute for Astronomy at the University of Hawaii at Manoa. Today, I'll be sharing with you all my research about the inner planet-forming regions of circumstellar disks. To begin, I'd like to speak a bit about the process by which planets are formed. First, we start with a massive cloud of gas and dust in space. Over time, this will begin to gravitationally collapse in on itself, compressing and heating until it finally forms what is called a protostar, or the precursor to a normal star. This protostar is then enshrouded in an envelope of gas and dust that further compresses into a circumstellar or protoplanetary disk. Planets begin to form from this material as the disk dissipates, until finally we are left with planets around a star, much like our own solar system that we see today. I'm particularly interested in this protoplanetary disk stage of planet formation, as these disks set the initial conditions for the formation and evolution of exoplanets. Instruments like the Atacama Large Millimeter Array in Chile, or ALMA, have captured beautiful images of these objects, and you can see within them rings and spirals, presumably caused by planets that are forming and carving out their orbits. However, we begin to encounter a bit of a problem when we compare our observations of protoplanetary disks with those of observed exoplanets. Here on the left is a plot of all observed exoplanets to date, and their separation from their host star is on the x-axis with planet mass on the y-axis. As you can see, the vast majority of exoplanets discovered lie within 10 AU of their host star, where an AU is defined as the distance between the Earth and the Sun. However, when we compare this inner 10 AU region with the beautiful maps that we see from ALMA that I'd previously shown, we can begin to see that we can't resolve any substructure that is actually located within the region that we expect to see exoplanets. This calls into question our ability to accurately predict planet formation pathways, as our start and endpoints for our observations don't seem to correspond to the same physical regions. To circumvent this, my research focuses on infrared spectroscopy of protoplanetary disks. From 4.5 to 5.5 microns, or roughly the x-axis of this plot, gas is excited to temperatures that correspond to the region within the inner 10 AU of disks. This gas then emits a variety of molecular spectral lines. From these lines, we can use techniques such as spectroastrometry and radiative transfer codes to estimate the amount of material that is present within the inner disk, or its column density, as well as estimating the temperature, emitting area, emitting radius, and other kinematic information about this region that is otherwise inaccessible. Due to the University of Hawaii's partnership with Mauna Kea telescopes, I specifically am fortunate enough to have access to high-resolution ground-based spectrographs for which I can conduct my research. While this type of spectra is incredibly useful on its own, it also happens to have an inordinate amount of synergy with other types of exciting astronomy that is happening today. I'm sure that we've all heard about the launch of the James Webb Space Telescope, or JWST, and that we've seen some of the beautiful images that it is currently taking. However, in addition to taking images, JWST also takes spectra similar to the ones that I've previously shown. Here's a plot comparing JWST spectra in black to ground-based spectra in gray for the exact same object. As we can see, the JWST spectra is much lower resolution, and we begin to lose information about individual line transitions, which makes our estimates of physical properties like temperature and emitting area much more uncertain. Therefore, ground-based spectra, like the ones that I collect and analyze, are crucial to properly interpret and understand the revolutionary new JWST data that is being taken. In addition to collaborating with JWST, I am also directly involved with programs that use ALMA, the large telescope that I had previously mentioned. By combining my observations of spectral observations of the inner disk with ALMA maps of the outer disk, we can begin to track how material may migrate from the outer to inner regions to form planets. Additionally, tracking this movement of this material may start to reveal clues as to how water arrived in our own solar system, and therefore provides us with a link as to how life may have formed here. Thank you so much for your time and attention, and please let me know if you have any questions.